Experiment 2.1, the acceleration due to gravity is the same for all objects. Supplies, we need safety goggles, he's got on his glasses, a large, heavy book, and a small piece of paper about 10 centimeters by 10 centimeters. We have all of that. Good job. All right, step one. Hold the book in one hand and the paper in the other at arm's length and make sure that they're at exactly the same height. Good job. Make sure that there are no obstructions beneath the two objects so that they can fall to the floor without running into something. All right, we're good. Ready? Step two. Release them both at precisely the same instant. And what happens? Level out the book, Jake. Keep them, get the paper at the same height. Okay, that looks good. Now go ahead and drop them.
3, 2, 1.
All right. All right, the book definitely hit first. No surprise there. All right, number 3, pick up the paper and the book. Step 4, this time place the piece of paper on top of the book and hold the book out at arm's length with both hands. All right, now release the book. And what happened? All right, what happened in the experiment? Well, when you drop the book and the paper in the first part of the experiment, the book probably hit the ground much earlier than the paper. This might lead you to conclude that the paper experiences a smaller acceleration due to gravity than does the book. However, in the second part of the experiment, the piece of paper stayed on top of the book, falling just as fast as the book fell. Why did this happen? The paper was not stuck to the book, therefore it did not have to stay on the book. If it were really experiencing a smaller acceleration due to gravity than the book should have started traveling faster than the piece of paper, eventually pulling away from it. Instead, they both fell at exactly the same velocity. Why? The explanation has to do with something we call air resistance. You see, when an object falls through the air, there are several gaseous molecules like nitrogen and oxygen, and atoms like argon that are in the object's way. In order to fall, the object must shove the gaseous molecules and atoms out of the way. Resistance. Well, the molecules and atoms resist this movement, and thus the object must force its way through them. A heavy object is much better at doing this than a light object. Therefore, heavy objects fall faster than light objects, not because their acceleration due to gravity is larger, but because they are not as strongly affected by air resistance as light objects are. The fact that light objects are affected by air resistance more than heavy objects is illustrated by the first part of the experiment. When you held the book and the paper in each hand and dropped them, they were both subject to air resistance. Since the paper was much more affected by air resistance than the book, it fell more slowly because it had a harder time shoving through the molecules and atoms in the air. When you place the paper on top of the book in the second part of the experiment, however, the book shoved the molecules and atoms in the air out of the way. The paper, therefore, did not have to. As a result, it was not subject to air resistance. Under those circumstances, then, the paper and the book fell with the same velocity, demonstrating the fact that gravity accelerates all objects equally. So let's go ahead and make sure we get that. Gravity accelerates all objects equally. What we learn from this experiment then is that when we neglect air resistance, all objects falling near the surface of the Earth accelerate equally at 9.8 meters per second straight down. We will discuss air resistance in a bit, and you will explore factors other than weight, which affect how strongly air resistance acts on an object. For now, however, I want to concentrate on free fall. Therefore, we will always neglect air resistance when solving problems that involve objects falling near the surface of the earth. For most of the objects we drop, balls, rocks, coins, etc., this is a reasonable thing to do because air resistance does not affect these objects very much. In fact, any object that is affected greatly by air resistance cannot experience free fall when dropped near the surface of the earth. After all, remember the definition of free fall. It tells us that in order to really experience free fall, the object must be falling solely under the influence of gravity. Air resistance produces an influence other than that of gravity. Thus, objects significantly affected by air resistance do not experience free fall when dropped near the surface of the earth. Since we are neglecting air resistance, then, when an object falls near the surface of the earth, we will consider it in free fall. Once again, this is only an assumption because all objects are influenced to some degree by air resistance. However, if this effect is small, then free fall is a good assumption. In the end, then, we will assume that objects falling near the surface of the earth are not greatly affected by air resistance. This means that the objects are in free fall. If that is the case, then all of the one-dimensional motion equations apply to the situation. It also means that we know the acceleration, 9.8 meters per second squared, or 32 feet per second squared straight down. Okay, now that we know the assumptions we will use while analyzing free fall, let's see how we can apply the equations we have already learned in order to find out something useful. For example, have you ever wondered how fast you can react to something that happens? Suppose you are driving a car and suddenly see an obstruction in the road ahead. How long will it take you to recognize the obstruction and move your foot from the accelerator to the brake? The time it takes you to do this is called your reaction time. As you might imagine, reaction time is different for different people. Some people react very quickly and they make good race car drivers, airplane pilots, and tennis players. Other people just can't react quickly, and such fast-paced professions are not for them. Using the concept of free fall and our equations of one-dimensional motion, you can perform the following experiment to measure your own reaction time. Experiment 2.2, determining a person's reaction time. Supplies needed are safety goggles, a ruler, preferably metric, and another person to help you. Get your helper to hold onto the ruler at the very top. Have him hold the ruler vertically with his arm held straight out. You should stand facing your helper slightly less than an arm's length away from the ruler. Take your right hand, or your left one if you're left-handed, and hold your thumb and forefinger about 3 centimeters apart as if you are ready to pinch someone. Hold your hand so that the middle of the ruler is directly between your thumb and forefinger, and so the one side of the ruler faces your thumb while the other side faces your forefinger. Line your thumb and forefinger up with one of the marks on the ruler and remember what mark it is. Once you're all set, tell your helper to release the ruler without warning you. The ruler will begin to fall. As soon as you notice it falling, grab the ruler by pinching your thumb and forefinger together. Now, look at the mark on the ruler where your thumb and forefinger ended up grasping it. Determine the distance in centimeters between this mark and the mark with which you lined up your thumb and forefinger. Repeat this experiment 5 times and average the results. In the end, you will have the average displacement through which the ruler fell before you grasped it. We can use this displacement to determine your reaction time. Do the entire experiment again, this time having your helper grasp the ruler while you drop it, and then put everything away. This is the data table for person 1 and person 2. Now that you have the average displacement of the ruler as it fell, we can determine the time it took for you to notice that the ruler was falling and grasp it with your thumb and forefinger. What was the initial velocity of the ruler? Well, since your helper was holding the ruler still before he dropped it, the ruler had an initial velocity of 0. So V naught equals 0. Once your helper released it, however, the ruler was in free fall. So the acceleration was 9.8 meters per second squared. You also determined the ruler's displacement before you were able to recognize that it was falling and grasp it. Using this information, you can determine the time that took. How? Well, we have the initial velocity, the acceleration, and we have the displacement. We're going to use person number 2's 14.8 centimeters. So, we want to determine the time. Which of our 3 equations can help us get there? I think we should use, so let's say time is unknown. We have to figure out what the time was. Delta x equals V naught t plus 1/2 a t squared. Before we do this, though, we need to make sure that the units are consistent. We have a problem with centimeters and we have meters up here. So you measured the distance the ruler fell in centimeters, but the acceleration is in meters per second squared. These units aren't consistent, so we must convert one of them. Well, the acceleration of 9.8 meters per second squared is the same as 980 centimeters per second squared. So we can go ahead and just switch that here if we want. We can use that value of acceleration because it is consistent with the distance that we measured. Now we will put in the quantities that we know and rearrange the equation to solve for time. All right. So we know displacement. We know V naught is 0. So anything times 0 is 0. So that term drops out. So if we want to simplify it a little bit, we can. Delta x equals 1/2 a t squared. Now we're trying to solve for t. So by doing that, we have to get rid of the half over here so we can multiply both sides by 2 and divide by a and take the square root and we get t. So t equals plus or minus the square root of 2 times the average displacement over 980 centimeters per second squared. So we get t equals plus or minus the square root of 2 times 14.8 centimeters over 980 centimeters per second squared. Our centimeters will cancel out. I had to pause the video to get a calculator. So my answer is t equals 0.17379325151 seconds. Obviously, that's way too many significant figures. So we have 2 significant figures here and 3 here. So this has to go down to 2 significant figures. So the answer is t equals 0.17 seconds. Do you see how to analyze free fall? Really, it's no different than what we've been doing, except that in the case of free fall, we always know the acceleration, 9.8 meters per second squared, or 32 feet per second squared. So we can analyze free fall situations the same way we have before, but the problems do not have to give us the acceleration because we already know it. Study the next example and solve the on-your-own problems that follow to be sure you understand. 2.7. How long will it take a rock to hit the ground if it is dropped from the Leaning Tower of Pisa, which is a height of 54.6 meters? All right, so we're given, it's in free fall because it's falling near the surface of the earth, and we neglect air resistance. So the acceleration is negative 9.8 meters per second squared. And we use the negative sign here to indicate that it's going down, downward motion. The displacement is negative 54.6 meters, again, because the object is being dropped off of the Leaning Tower of Pisa, which has a height of 54.6 meters. The initial velocity, or v naught, is 0 because it is dropped. So what are we trying to solve for? How long will it take? So that's time. How long will it take? We're trying to solve for time. So we have to figure out which equation to use. We decide to use the displacement equation. Delta x equals v naught times time plus 1/2 at squared. Again, if it's dropped, its initial velocity is 0. Anything times 0 is 0. So this just drops out. So we have delta x equals 1/2 at squared. We need to solve for t. So t is the square root of plus or minus 2 times the displacement over acceleration. So here we go. We put in the negative 54.6 meters times 2 over negative 9.8 meters per second squared. Again, we just multiplied those two together. The meters cancel out. Then we get the answer of 11.1428 seconds squared. Obviously, we realize that's too many significant figures. The limiting one is 2 here, 9.8. So we have a answer here of 11 seconds. So then the square root of 11 seconds is plus or minus 3.33766 ... Too many significant figures. If we have 2 here, we can only have 2 here. So it takes 3.3 seconds for an object to fall from the Leaning Tower of Pisa. And lastly, 2.8. In order to determine the height of a bridge, a physics student drops a rock off the side of the bridge and times how long it takes for the rock to hit the water. If it takes 1.4 seconds for the rock to hit the water, what is the height of the bridge in feet? So once again, we always have to figure out what's given. We know it's in free fall, so we're ignoring air resistance. V naught is 0, once again because it was dropped. The acceleration, because it's in free fall, is negative 9.8 meters per second squared, or negative 32 feet per second squared. Once again, I think we're going to use the negative 32 feet per second squared because the answer is asked in feet. And it's negative simply because it's being dropped. We know the time, it said 1.4 seconds. So we're just trying to get the height or the displacement. So the equation we're going to use is delta x equals v naught times time plus 1/2 at squared. V naught being 0, initial velocity of 0. This cancels out. So we're left with 1/2 times 32 feet per second squared times 1.4, the time squared, which is 1.96 seconds squared. The seconds cancel out, and we're left with a delta x, or a height, of negative 31.36 feet. That's the wrong significant figures. We only have 2 significant figures here, so the answer can only have 2 significant figures. So the answer is negative 31 feet. That's how far the rock fell. So the rock traveled down 31 feet. So the bridge has to be 31 feet above the water.